Okay. Hey everyone, today we're going to be exploring uniform circular motion and gravity. So first up, we're going to be talking about uniform circular motion. So uniform circular motion is a concept that we experience practically every day. And we're just going to play a really short clip of an example of such a motion, and then we'll just look at some of the details of it. So a really important details to notice in this video is that how the water does not spill when the bucket is traveling at a very large pace. And on the contrary, when the bucket starts moving at a slower speed, the water does spill out. So the question that we're going to explore is why doesn't the water actually spill when the bucket is at a high speed, and at the same time why it does spill when it's at a lower speed. So the answer to this is basically uniform circular motion. And in this concept, the motion is basically a constant speed, not velocity, because the direction is constantly changing, and in a circular direction. And this also means that the angular velocity is constant. However, a very important concept in this is that there is an acceleration, which is caused by a force pulling the object inward. And this is what this diagram shows here. So in this case, hypothetically, you can imagine this as a string, or like the woman in the previous video showed, it was her hand. And that provides a tension force in the direction below. And this force causes an acceleration in that exact direction. However, instead of pulling it downwards, it causes an acceleration, allowing the object to move perpendicular to this force.
And so to find the magnitude of this acceleration, we can basically take the square of the velocity or the speed and divide that by the radius. And the acceleration is not equal to the change in velocity over the change in time, because the acceleration works to change the direction of the speed, not to actually change the magnitude. And because the magnitude is constant, it's not going to be the change in velocity over change in time. And then we can use Newton's second law, which is F equals ma, to find that the centripetal force is mv squared over r. And so we have an important note here that the acceleration and force referred to above are perpendicular, so they do not impact the velocity's rate of a change. Instead, they just change the direction. And so we also have a simulation here that you can find in Google Classroom. We're not going to play it now, but feel free to play around with it on your own time. And so as we mentioned, the centripetal force is equal to mv squared over r, where the centripetal force is, as Tanvi mentioned, a force that's causing the object to swing in a circle. And usually it's like a kind of tension force, or in the video, it was an applied force by the hand. And so from this, we can see that velocity squared is proportional to r. And so that means that if you were to increase the velocity, the radius of the circle must also increase in order to maintain circular motion. So basically, if you want to keep spinning faster and faster, to have to apply the same force, the radius has to increase. So we have an example here of a lasso. If you were to decrease the speed at which you were turning it, it'll fall inwards and not be a circle. But if you decrease the speed along with the radius, the circle is maintained.
And adding on to the idea of centripetal motion, a lot of people associate an opposite force completely in the opposite direction of centripetal force and label that as centrifugal force. And it's considered that that force pushes us outward, allowing the movement to be balanced. However, this notion is false, and it's very important to recognize that it is false. There's actually no force pushing you outwards. Instead, it is just the concept of inertia. And as per Newton's first law, which we explored a couple weeks ago, every object will continue in the same direction with the same velocity unless acted upon by an unbalanced force. And if we look at this diagram over here, you can see how the ball has a trajectory of completely straight, and that is its inertial path and the path that it wants to continue on. However, due to the centripetal force, it is pulled inwards, creating that circular path. But the ball feels as though it is being pushed outward because it desires to move in this straight path. And we're also going to talk about the amusement park problem. And this idea and this problem is very common on the AP because it deals with the change of force and its direction. And we can think about this as like going on a roller coaster. And the object is not necessarily in uniform circular motion because its velocity is always changing because the centripetal force is changing because there are different forces acting upon it. If you look at the bottom, gravity is, in all of these situations, gravity is pointing downwards. That's because that's the only direction gravity will point in. However, a normal force will be perpendicular to the platform that it is on. So at the bottom, it's pointing up, and at the top, it's pointing down. And because of these varying centripetal forces, because if you see here, at the top, the centripetal force is gravity plus the normal force. While at the bottom, the centripetal force is the normal force minus the gravitational force, and therefore it is different. But the radius is constant. And therefore, in order to maintain that centripetal motion to ensure that the roller coaster does not fall off, the velocity must change accordingly. So in order to do that, we'll practice this more often. The net force, which is the centripetal force, changes consistently.
So now that we've covered basically all the formulas and all the topics that are in centripetal motion, we'll go through a couple practice problems that you might see on the AP. The first one is a Lincoln Continental and a Yugo are making a turn. The Lincoln is 4 times more massive than the Yugo. If they make the turn at the same speed, then how do the centripetal forces acting upon the two cars compare? Explain. And so I'll give you maybe 5 seconds to pause the video and come up with your own answer, and then we'll come back to it. So this is a really straightforward problem in that we just have the centripetal motion is equal to mv squared over r. And so we know that if the Lincoln is 4 times more massive than Yugo, and they turn at the same speed, we can just plug in, for Lincoln would have 4m, whereas for Yugo we just have m. And since v squared over r will be constant, we know that the Lincoln will have at least 4 times the centripetal force of the Yugo. So it's a very straightforward problem. All we had to do is substitute 4m for m in this problem. For the second problem, we have a ball attached to a string, which is 1.5 meters long. It is spun so that it completes 2 full rotations every second. And what is the centripetal acceleration felt by the ball? And so again, I'll give maybe 5 seconds to pause the video and come up with an answer. And once you've gotten it, we can go over the solution. So we know that the acceleration is equal to v squared over r, as is defined by centripetal motion. Now, we also know that velocity is basically distance over time. And in this case, we have distance over time can be written as the total distance of a circle is 2 pi r, or its circumference. And over time is frequency. And frequency and period are two quantities that are often related with centripetal motion. So period is basically the amount of time it takes to complete 1 full revolution, whereas frequency is how many revolutions you can complete in a second. So basically, the circumference is the distance over period is time. And it's worth noting that period and frequency are inverses. So 1 over period is frequency, so that's how we get 2 pi r times frequency. Or in other words, the velocity is equal to 6 pi meters per second. And so now we have the circumference, we have the velocity, we have acceleration equals v squared over r. And so we can just plug these equations in as velocity is 6 pi squared, r is 1.5 meters, And solving, we get 237 meters per second. And that's basically all for centripetal motion.
Now we're going to go into gravity, and the concepts are overlapping, so it should be pretty straightforward. So similar to the video before, let's take some time to identify what is gravity. And you experience this every day, but it's helpful to have a video of it. And the main idea of this video is to identify that the bowling ball and the feathers drop at the exact same rate in a vacuum. And more traditionally, you would think that the bowling ball would fall faster because it's heavier, but that isn't necessarily the case, and we'll explore this more. So this comes from Newton's universal law of gravitation, which basically says that gravity is the attractive force between any two objects with mass. And you can calculate this force using a formula that you'll be using very often on the AP, which is that the force of gravity is equal to a gravitational constant times the first mass times the second mass, all divided by the radius, or the distance, which is r, squared between these two objects. And the gravitational constant is 6.67 times 10 to the negative 11th meters cubed divided by kilograms times seconds squared. And it's a very complicated constant, basically just to balance out all of the units and variables in the equation. And from this equation, it's also important to note the relationships between all the variables. So the force is directly proportional to the product of the masses, and it is also inversely proportional to the square of the distances between the center of masses. And it might sound really complicated right now, but once you understand the equation, these concepts become really helpful when trying to understand several problems.
So moving on to gravitational field strength. And this is kind of the model for why is there gravity and how does it work? And the actual reason for this is that we see that all objects attract each other through a gravitational field. And this field is caused by objects kind of warping a space-time continuum and attracting each other in that way. And that's actually beyond the level of AP Physics 1, but it kind of explains why not only am I attracted to the Earth and the Earth attracted to me through gravity, but I'm attracted to a hamburger in McDonald's, for example, or a nearby book. So everything in the world is attracted to each other. But why don't we feel the effects of that, right? We only feel it when we fall down to Earth because that's because Earth's mass is so big. And why don't I feel an effect with a hamburger? Well, the reason comes back to G, which is, as Tanvi mentioned, 6.67 times 10 to the minus 11. This is actually measured by Henry Cavendish, and what he did was a nice experiment where he took two balls and kind of hung them apart, and he had very accurate measurements to kind of find out that it was such a small value. And because of that super small value, we usually don't feel these effects. But for AP Physics 1, what we need to be concerned with is that the acceleration will be equal to the force of gravity over mass from Newton's second law. As Tanvi just mentioned, the force of gravity will be gmm over r squared. And one of the m's will cancel, so you get the acceleration will be gm1 over r squared. And so let's look at the radius of Earth as r and the mass of Earth as m1. Now, if you plug this in, 6.67 times 10 to the minus 11 times the mass of Earth divided by r squared, you'll actually find that the acceleration is 9.8 meters per second squared. That's the lowercase g that we always mention before in kinematics and 2D projectile motion. And so now we can look back at the video we watched earlier and contemplate, why do objects fall at the same rate? And the reason is that we don't have m2, we just have m1 in this equation. A equals to g m1 over r squared, where m1 is the mass of Earth and m2 is the mass of an object. So for example, m2, which is the mass of a hammer, is not in the equation, just as m2, the mass of a bowling ball, is not in the equation, just as m2, the mass of a feather, is not in the equation. The only things that matter are the distance from the center of the Earth and the mass of the Earth. So the acceleration will be the same for all objects. The next topic is Kepler's 3 laws, and these are once again related to gravity. These are actually like a little bit beyond the scope of the AP test in that it's actually covered on the AP exam. It's covered in most classes, but the AP usually doesn't get very specific about each law. They just generally kind of test vaguely about it. And so we have 3 laws. The first one is the law of ellipses. This is that planets that orbit the sun travel in an ellipse. The sum of the distances from every point is a constant. And basically what this is saying is that Earth does not travel around the sun in a sphere, and Earth does not travel neither does Mars, and that's basically the law of ellipses. The law of equal areas is basically the area formed by, it's not actually triangles. Triangles is an approximation, but area formed by triangles in an orbit are the same for equal periods of time. So what that means is when the Earth travels around the sun from point A to B, the area it sweeps out, for example, one green region, will always equal the area swept out by another region in the same amount of time. So if the Earth is on this side of the sun and in like 20 seconds it sweeps out some area, on the other side of the sun, even though it's an ellipse and not a perfect circle, it might travel further and be closer. That kind of sweeps out the same area. So what that says is basically at any time the same area will be swept out, or by Newton's law of gravitation, a smaller radius. So if you're closer to the sun, you have to travel faster, and if you're further from the sun, you'll travel slower to sweep out the same area. That's also kind of related to the law of conservation of angular momentum, but that'll come in a different lecture. The final law is the law of harmonies, and this states that t squared is proportional to r cubed for all for all planets in a solar system. And t squared, as we mentioned, is period squared. So that's the total time to go around in a full orbit, in a full ellipse. On Earth, that's usually 365 days. And r cubed is the distance. And so it's a constant for every planet orbiting the sun. So what that means is that for Earth, t squared over r cubed might be some number, but that number will be the same for Neptune and the same for Mars. Basically, it's the total time to go around for Mars divided by its distance from the sun. The total time to go around the sun for Mars squared divided by the distance cubed will be the same as Neptune, and that's the law of harmonies.
So now we're going to go into some problems related to gravity. So the first one is, a certain planet has 3 times the radius of Earth and 9 times the mass. How does the acceleration of gravity at the surface of this planet, which we will call a sub g, compare to the acceleration at the surface of the Earth, which as usual we will call g? So like before, we'll give you around 5 seconds to pause this video, give it a shot, and then we will go into the answers. So for the solution, the first step is to identify that the acceleration is given by this equation, the gravitational constant times the mass divided by the radius or the distance squared. And when we plug it in for Earth, we can just, instead of plugging in the actual numbers, we can just leave it as variables. So the mass of Earth and the radius of the Earth. And in this case, that we can just label as g because that's what we know it resolves down to. And when we do the same thing for the second planet, we can put 9 times the mass of Earth and 3 times the radius of Earth. And as we simplify down the equation, we can see that the 2 9s here cancel out, and we result in the exact same equation as we did for Earth. And for this very reason, interestingly, the acceleration of a sub g of the second planet is exactly the same as that of the Earth, even though it has a different mass and a different radius. And now our second problem. 2 satellites in space, each with a mass of 2,000 kilograms, are 1,500 meters apart from each other. What is the force of gravity between them? And like before, again, we will give you 5 seconds to just pause this video, try out the problem, and then we'll go through the answers. So first up, let's put down the equation for the gravitational force. It's the same old gravitational constant times m1, m2 divided by r squared. And if we just plug in the numbers, it's really as simple as that. We have the gravitational constant, we have the two masses, and we have the r, and then we square it. And you just plug into your calculator, plug and chug, and it resolves down to this answer. And that is your answer. It's just as simple as that. An important concept here is also to identify that the gravity for both objects is exactly the same. In this case, fortunately, the masses are the same. But even if, hypothetically, the second mass was, for example, 1,000 kilograms instead, the force would definitely be lower, but both the heavier mass and the lighter mass would experience the same amount of gravitational force.
And just quickly adding on to what Tanvi mentioned, the reason why the larger mass will not move as fast is because by Newton's second law, F equals ma, and since its mass is larger and they have the same force, its acceleration will be smaller. So it'll seem like it has a smaller effect, even though they have the same force. So another way of putting that is that the force of gravity on me from the Earth will actually be the same as the force of gravity on the Earth from me, and that's a direct consequence of Newton's third law. But now we're going to go to some applications of both of these concepts and why they're frequently tested as kind of one big unit on the AP. And so the first one is satellites. And this is what we just kind of hinted at in the previous practice problem. The satellites are, as it mentions, actually in constant free fall around the Earth. And at the velocity that they're traveling at, there's a perfect balance between the force pulling it inward and its velocity forward. Another way of putting that is there's a perfect balance between the centripetal force, which is actually the force of gravity, and its velocity force, and the velocity forward. So if we combine the concepts, the gravitational force from Earth is the centripetal force. And so again, as we mentioned, inertia would want the satellite to go straight on in a path kind of in the green arrow as mentioned before. But gravity does not change its speed as much as it simply changes its direction. And that prevents it from going straight to the Earth. It also prevents it from just flying off forever. And so now we're going to go to some multiple choice practice problems, kind of a mix of both topics covered today. So the first problem is an astronaut is in an orbiting spacecraft. He attaches a mass m to a string and whirls it around in uniform circular motion. The radius of the circle is r, the speed is v, and the tension is F. If the mass, radius, and speed were all to double, what happens to the tension to maintain uniform circular motion? And so again, we'll give another 5 seconds to pause the video and then come back. So again, this problem is a really straightforward consequence of centripetal motion. So we know that the force of tension will be equal to mv squared over r because it's what's responsible for keeping the ball in uniform circular motion. In this case, we double the mass, we double the radius, and we double the speed. So all we have to do is multiply each term by 2. So we have 2m times 2v whole squared over 2r. And 2v whole squared is actually 4v squared. So the whole thing will become 8mv squared over 2r, which is 4mv squared, which is equal to 4f. So we'd have to quadruple the tension force to keep everything, to keep uniform circular motion.
And now our second problem.
Yeah, and the second problem, Tanvi will take.
And now our second problem. A figure of a dancer on a music box moves counterclockwise at a constant speed around the path shown below. The path is such that the lengths of the sequence PQ, QR, RS, and SP are all equal. The arcs QR and SP are semicircles. And which of the following best represents the magnitude of the dancer's acceleration as a function of time during one trip around the path, beginning at point P? And this is the image right here for some reference. And also, just a key note, the diagrams here are not so clear, so the labels are T sub P, T sub Q, T sub R, T sub S, and again, T sub P right at the end. And we will give, again, just 5 seconds to give this a shot, and we'll come back with the answers. So in order to solve this problem, it's really important to first identify what is happening with the acceleration between P and Q. And if we notice here, it's just traveling in a straight line. And for that reason, if the object is moving at a constant speed, we can immediately say that the acceleration is just 0. And that allows us to cancel out both A and C. Therefore, we are left with D and B. And in this situation, we are told that it is always traveling at a constant speed. And therefore, we are allowed to assume that at point Q, the object immediately gains the acceleration due to the centripetal force, which allows it to travel in this circular path at a constant speed. And we can see that the radius here would be a constant in this area from Q to the center point around the circle, and at the same sense in this circle, this semicircle. And therefore the acceleration is constant, but not 0 between Q and R, as well as S and P. And therefore we can rule out D, and we get the answer as B. It is important, however, to recognize that in real life, obviously this doesn't happen, and you will have to accelerate a certain extent to allow yourself to gain the velocity required. And the force, which oftentimes won't be as instinctive to notice, is actually the frictional, if you're hypothetically in a car, but in this case, obviously it's a figure of a dance in a music box, you can think that it's a frictional force. And that's what's pulling you towards the circle, which is creating that centripetal force. And in this case, you can think about it as probably being some sort of applied force. Of course, it's not really labeled in the problem, but that's what you can think about. And when we're working through such problems, it's usually helpful to just recognize which force it actually is. And now our second problem. An object shown in the accompanying figure, right here, moves in uniform circular motion. Which arrow best depicts the net force acting on the object at the instance below? This has no math, so just pause it for a sec, give it a shot, think about it, and we'll get you the answer. And like I mentioned before, this doesn't have any math, and it just tests your understanding of the concept. And it's important to recognize here that it is, in fact, B, because as we mentioned before, the centripetal force will always be pointing towards the center of the circle, which is right about there. And therefore, no matter where it is, the velocity will always be pointing towards the center of the circle. And therefore, we can get that the answer is, in fact, B.
And so that concludes our class. We can give like a really short review in that acceleration in circular motion is v squared over r. Force is mv squared over r. Period, which is the total time to go in total time to complete a circle or a loop, is 2 pi over the velocity, and frequency is the inverse of period. And then turning to in centripetal motion, the force always points towards the circle. Then we can turn to gravity, where we learn that the force is equal to g mm over r squared, where g is 6.67 times 10 to the minus 11. And we also learned that for objects on Earth, we have the force is equal, acceleration is equal to gm over r squared, which is also equal to lowercase g, or 9.8 meters per second. So we also have some additional resources if you're interested in learning from physics classroom, from also some practice problems on centripetal force and acceleration and on gravity. I know we only did like 5 this time, but there's still plenty available on Google Classroom as well.
Thank you so
for
much.
watching.